I'm really pleased to be here, and also pleased that it's very kind of Jason to introduce me like that. Usually he just introduces me as the other Jason. But as you know, Intel's been involved in open compute for quite some time, actually since the inception. And there are times where I get asked, why is it that Intel is so committed to open compute? What do we want to see the community achieve? And the answer is really simple. This room is absolutely critical to shaping the way we see the industry evolving over the next several years. And let me tell you what I mean by that. There's an overarching move to scale computing. And it doesn't mean necessarily everything's going to be hyperscale. But when we look out about 10 years, we think that more than 70% of all the systems that are consumed in data centers will be consumed by data centers that have some semblance of scale. Thousands of systems, compute, network, and storage coming together. And the reason for that is not just the rise of cloud computing and mega-scale data centers, but we also see comms service providers, many of you who are here in the room today, seeing interest in needing to deploy systems efficiently at scale. SaaS providers, gaming companies, enterprises that may have some sort of large service to go deploy are all coming to us and saying, we know that we need to have this capability to efficiently deploy services and as a result data centers at scale. And this is not easy to go do. And that was the thing that really sort of inspired us to join Open Compute in the first place, is we knew that it was an incredibly generous thing that Facebook wanted to be able to share their best practices with the industry and help the industry grow and evolve. And since then, we've seen many other companies join in that effort and share their ideas and share this notion of open source hardware so that we can see efficiency occur in the industry. But this isn't going to come without effort. It's not going to come without a community around it. And we need to make sure that the way we get the industry to achieve this sense of scale is by doing it in a way where we can deliver at scale systems that are easy and efficient to deploy. And we believe that at the heart of this move to scale computing, the fundamental rack, the fundamental building blocks of computing need to evolve. And that's why we've invested so much effort at Intel in the rack scale architecture. And the idea behind the rack scale architecture is that many companies want to deploy cloud computing efficiently. And it starts with that overarching layer of data center orchestration, which can be coming from, for example, a Microsoft Azure stack. It could come from a VMware Evo, OpenStack. It could be a Kubernetes combination with Docker containers. But that overarching stack needs to have an efficient way of managing the underlying hardware at scale. And pooling of resources is an essential concept to making sure that that occurs efficiently. And that intersection between what we see as those pools of compute, network, and storage up to that orchestration layer, we need APIs and we need an industry effort. And we've been very fortunate in being able to galvanize the industry behind this rack scale architecture effort. And you can see that it's not just the leading software providers that want to deploy their cloud stacks that are supporting the APIs, but we have a number of hardware vendors, and we're also driving standards like Redfish or Chinook in the industry to make sure that all this can come together. It's this type of effort that will really make sure that companies that want to innovate at scale have the ability to do so efficiently. Now, one of the concerns that I hear, and there's been some dissonance in the industry, is that, well, wait, should I be supporting rack scale architecture or should I be supporting open compute racks? And I want to highlight the fact that these two are complementary. That rack scale architecture was really designed to be a logical architecture. It's not designed to specify the specific form factors of the actual rack itself. And in fact, maybe it's not one rack, maybe it could be multiple racks. But at the end of the day, we want to make sure that these two are complementary. And so our ideal is that we're able to go work with the industry and the hardware vendors and the software vendors to help develop that architecture that creates pools of compute, network, and storage that can be efficiently allocated and managed. but then to be able to bring those physically to market in standardized form factors that can scale across the industry, that there's some level of consistency for those of you that are looking to build those scale data centers. And open compute is absolutely essential to making that happen. Now, in each of these areas, you need to have innovation in compute, network, and storage, and that's really why I'm here today. We've had, up until now, 18 different contributions that Intel has made through our history of involvement in open compute. And I want to highlight some of the new and exciting advancements that we're making across compute, network, and storage. So I want to start with what we're doing on the compute front. And I hope, by the way, that we go way past these 15 minutes that I have with you, and that you're able to continue the dialogue with some of the folks from the Intel team in the booth and some of our partners like Quanta and WeWin and Hive and others about the technology that's being rolled out. But starting with something that's probably one of the most broadly used building blocks in data centers across the world, the 2-socket Xeon server is getting an upgrade this year through open compute. The 19-inch rack form factor was the decathlete board, and what we've done is recognize that more and more there's a need for larger memory footprints in the standard 2-socket servers. So the 2.1 spec you'll see has been enhanced, increasing the DIMM capacity from 16 to 24 DIMMs in this form factor. But we're also committed to making sure that as soon as we launch the Broadwell generation of our Xeon E5, that's the 14 nanometer product, that you're able to go ahead and take advantage of that in decathlete 2.1 as well. So stay tuned for those enhancements to the 2-socket server. But we also recognize that not every server is going to require 2 sockets and that amount of memory. And in fact, through our collaboration with Facebook, one of the things that we heard was that some of their workloads would actually prefer a more dense type of form factor, that a lightweight, highly compacted SoC might be exactly what they're looking for. And what I'm pleased to share with you today is that's what innovation and collaboration together can bring. I'm going to show you a quick photo of it. The camera's going to hopefully pop up here in a second. But this is what 16 cores looks like with integrated Ethernet. This is the power of 14 nanometer. This is the new and just introduced Xeon D, which has 16 cores, 1.9 gigahertz, 65 watts generated from this high-performing CPU. Now, bringing this innovation to the industry means that we have to have form factors and we need to have boards. And so this will be supported in the Mono Lake form factor. But Facebook was able to see from their previous generation a 40% performance improvement. And this product is not a lightweight atom core like we put into SoCs in the past. These are 16 cores, full Xeon cores with 10 gigabit integrated Ethernet. And if you compare the level of performance of this to our previous generation, it's a 3x improvement. So a tremendous amount of power and really allowing companies that need workloads for a dense application to be able to do this on an industry standard open compute Mono Lake board. We also recognize on the compute front that at scale, the acceptability and the desirability of workload acceleration is increasing. There could be algorithms for security or for machine learning that it's desirable to go ahead and put together an accelerator for. But we also recognize that a lot of those accelerators are still very early in its formulation, and that's where a FPGA comes in, is it allows those algorithms that are still in tuning to be programmable and to be able to be optimized over time. And that was part of the genesis that led Intel to acquire Altera. And what I'm pleased to actually unveil here today is that this is the first Xeon part that integrates the ARIA 10 FPGA into a single package together. And so this is bringing rapid innovation to market. We want to make sure that this part, which will start sampling in the first quarter of this year, will be able to be accepted into standard open compute motherboards. So you can expect we'll be introducing that innovation to be coming shortly and enhancing the motherboard specs to make sure that they are FPGA ready. The other thing that we want to do with the community is open source libraries. We recognize at Intel, probably better than most people, that RTL is not exactly the preferred programming language for everyone here in the audience. And so as a result, we want to make sure that there are libraries that are available for machine learning, for compression algorithms, for SSL. And we actually want the community to come to us and say, here are some things that we'd like to see accelerated. And we're planning to go make sure that those libraries are broadly available, they're supported within the open compute community, and that we not only have boards coming to market later this year around FPGA support, but we also have the software support that the community requires. So shifting over from compute onto network, one of the things that obviously is an implication of having an SoC and integrating Ethernet, and integrating Ethernet, by the way, into our chipsets and CPUs moving forward, is that the mezzanine spec, which was designed around PCI Express, also needs to evolve, that you want to be able to route traffic that takes advantage of integrated PHYs. And to be able to do that, you have to be able to support and route KR across the mezzanine spec. So the new Mezzanine 2.0 has an additional C connector that then supports the routing and support for KR, and is really ideally suited to integrated Ethernet into an SoC or into a chipset or something else in the platform. So we're making sure that we're evolving these network specs to scale. Another element of that enhancement is the move to silicon photonics. And one of the things that separates what you see in the mass market and the general computing community from what we see at hyperscale is the speed of the network. While many of the folks in the industry are still transitioning from 1 gig to 10 gig Ethernet, many of the cloud service providers are planning to start adoption of 100 gig Ethernet this year. So you can see an order of 10x magnitude in the requirements for high-speed traffic. And that becomes additionally difficult at a large data center scale. And that's why silicon photonics is so desirable and is going to become a requirement within the data center very shortly. Now that doesn't mean that we don't have the need to be able to make enhancements quickly. We do need to drive down the cost and increase the bandwidth of photonics. But we're hard at work at doing that. What you see here is the standardized connector. We're very pleased that we've taken a very open approach to silicon photonics. We are working with open standards industries like the CLR4 Alliance to make sure that there are standard connectors out there in the industry. We actually did that, by the way, with our partners at Arista starting back in 2014. So we want to make sure that the industry is ready to be able to adopt silicon photonics. And as part of doing that, what you'll see in the future is as we move from 100 gig to 400 gig silicon photonics, to get that type of cost reduction, we'll be moving away from a connector base to actually going down onto the platform itself. And that'll be something we'll be working very closely with the community here to make sure that there are boards, systems, standards available to make that happen. And one of the things that makes our approach to silicon photonics unique is that we have true wafer scale integration. Manufacturing where the optic emitting or the light emitting part of that laser structure is in the silicon itself. And so we've designed with the end in mind cost-effective silicon photonics that can scale, and working very closely with the industry as a whole to make that happen. So obviously we've talked about compute and network, and there's a huge amount of innovation that's required to make that happen, but we certainly can't leave storage behind at the same time. So what you see here is that one of the big innovations in storage is obviously the move to non-volatile memory. The fact that a solid-state drive now with PCI Express can deliver 6x the level of performance that it was able to go do before. And what we want to be able to do is take the performance value from NVMe and the bleeding edge technology and combine that with the density and the capacity that's required to be able to drive innovation and support storage requirements for companies that do data centers at scale like Facebook. And this is yet another example of an innovation that's come together through that type of collaboration. What you see here is the 2U Lightning spec, which we're very pleased to be able to introduce today. You've got two different trays, as you can see. Each of these trays can support up to 15 drives. If these drives have 4 terabytes of NVMe in them, you're looking at a total of 120 terabytes densely packed into a 2U form factor. And what that then also can go drive is a tremendous amount of I/O throughput. You're looking at up to 2.5 million IOPS delivered through this platform. So we need to make sure that we're driving across compute innovation, network innovation, and storage innovation to allow companies to deliver data centers at scale. But I can't leave behind the fact that we need software on top of it. And I'm also pleased to be able to share two very key projects that make sure that these racks and these systems at scale can be managed and we can see analytics that come from them. One I want to make you aware of is an open source telemetry framework called Snap. This is something that you can see through GitHub, and we'd like to see more of the open compute community contribute to it. One of the things that makes it very unique is it allows you to aggregate all of the telemetry coming off of the Intel platform in a very seamless manner. But the other thing is it's designed for continuous uptime. A lot of telemetry, a lot of analytics solutions require you to make changes and then offline and reconnect the system. Snap is designed for real-time innovation, real-time management, and making sure that all the time you can be able to do processing on the telemetry coming off of the platform. So this is a project we're very excited about to allow companies to manage all the compute, network, and storage at scale. And this then ties in with an analytics framework that Intel has open sourced to the industry, something called TAP, which is the Trusted Analytics Platform. And the idea behind this is allowing and greatly simplifying the route from connecting data sources to processors, to machine learning, to other analytics, and the ability to write code and easily deploy it at scale. So we're excited that this also provides a combination of analytics in conjunction with the Snap telemetry to allow new innovation in managing data centers at scale. So let me wrap up because I know I'm out of time. The data centers are changing. Everybody needs to be able to deploy at scale if IT is critical to their business. And to do that, we as the community have to make sure that the building blocks are efficient across compute, network, and storage. And it's not just enough to produce those systems. We need software that allows you to be able to integrate that into orchestration frameworks, to manage telemetry, and to do analytics on the performance of that overall structure. We're committed to making that happen. I'm very, very grateful to be here and be a part of this community, and I hope to continue the dialogue and see you at our booth and alongside our partners later on today. Thank you.